Let's let's start getting a better idea about our logarithmic functions, particularly those with the base e or base 10. Okay, so we have that uh, the basis of the log functions has its roots in the exponential function. So if we look at y equals 2 to the x, what we know about that and what we know about any exponential function, that it is one to one, which of course is necessary for the function to have an inverse, which is a function. Okay, so yes, the functions, the inverses of exponential functions are what we're going to examine, and what we should know is, of course, that they are in fact logarithms. Um, so looking at the inverse of y equals 2 to the x, it is x equals 2 to the y. But obviously, that presents a problem in that we cannot isolate y, write y in terms of x, or write it in our typical function notation. And henceforth, we needed to come up with a method, which is what logarithms does for us. So uh, the expression x equals 2 to the y can be written as a function by rewriting it as y equals log base a of x, or in general, if we were talking about base 2, that would be log base 2 of x. But okay, so for a generalized function, x equals a to the y, it is written as a function y equals log base a of x, and that is the very basis of logarithms, is knowing how to go back and forth from an expression of this form, log base a of x, to x equals a to the y. They're um, one in the same. Okay, a to the y equals x is the same as log base a of x equaling y. Okay. What we should know about these log graphs, and we're going to limit it to the log functions for a values greater than 1. Well, again, being the inverse of an exponential, let's go back to the exponential. Exponential y equals 2 to the x. Well, we know that it could take on every value of x, which of course says that the domain is all reals, but then it only was graphed in the upper two quadrants, which was to say the range was only positives. Okay, well, then when you take the inverse, you flip the domain and the range, and therefore we find for any log graph, the domain is, okay, only positives, and the range is all numbers. Um, it does contain, since our exponential functions all contain the y-intercept of x, our logarithmic functions should all contain the x-intercept of 1. Okay? And since the exponential functions were uh, asymptotic to the negative x-axis, our logarithmic functions will be asymptotic to the negative y-axis. Okay? Um, Recalling these generalizations can be safely assumed when reflections and translations are imposed, okay, that there's the same impact, okay, moving it left, right, up, or down. Um, we can say the same thing is going to happen all when we consider the values of a between 0 and 1. So aside from the above, graphs of log base A are easily defined and easily graphed, because basically you have an intercept and an asymptote, and you have the flow. And of course, we'll look at those in greater detail. Okay, what we want to do again here is our very basic idea. Y equals log base A of x is almost always, for cases of problems, translated into a to the y equals x. Okay. And we have a couple things here that we want to emphasize. Common logs are logs base 10. Okay, in other words, um, the log base 10 of x, okay, implies 10 to the y equals x, but it is a common log. It's anything base 10, you don't need the subscript. You drop the subscript, okay? It just becomes just the log. Y equals the log of x, and you'll see those keys on your calculator. Log, okay? It just means log base 10, okay? Drop the subscript, okay? I'm trying to get that point across, okay? The natural logs are the logs base e. So when we're looking at, okay, a log base e, y equals log base e of x is the function y, then, okay, again, it's one that's used so often, okay, you drop the subscript. Of course, you've already dropped the subscript, so we discern the natural log, which is the log base e, with the notation ln. So this can be read y equals the ln of x, or y equals the ln of x, or y equals the natural log of x. You know, if you don't like the drop subscript, you can write it over here, but this is the way you're going to see it almost every time. Okay, we did review some of these again. Let's take a look. Y equals or rather log of 1.5 of 27/8 is equal to y. Immediately we change it. 1.5 to the y is equal to 27/8. Then it becomes an exponential equation, the likes of which we've already seen. What about this expression? The natural log of e to the 47th is y. Well, again, the natural log of e is the log base e of e to the 47th. And what's this translate into? This says e to the y is equal to e to the 47th, which is, of course, saying y equals 47. Here's one where we have to find the base. So this translates into x to the 5th is 9 the root of 3. Now this is kind of a unique problem because, again, we're trying to, in this case, solve for x. So we're going to look at this expression over here, 9 root 3, because there's really nothing you can do with x to the 5th. So 9 root 3 is, of course, 3 squared times 3 to the half, which is 3 to the 5 halves. Okay, and on that basis, we come and we're able to say, well, if I took the fifth root here, okay, then that would eradicate this fifth power and just turn it into x, and then invariably we see that x is equal to root 3. And here's an interesting problem. I think you might like this. Log, oh, come on, back here. Log of the log of the log of x equals 10. Equals 1, excuse me. Okay, so this it looks like a composition of functions, which is exactly what it is, but we want to evaluate it, so we want to move from the inside out. So it looks very complicated, and we're just going to say, come on, stop that. We're just going to say, look over here, okay? Let this whole log of the log of x, that whole inner expression there, just be p. So then what we have then is, looking down here, we have just the log, and of course log with no subscript is, log base 10. So this is log base 10 of p equals 1, right? Which immediately you translate to say, well, 10 to the first is what p is, which is 10. So now we've determined that p is 10, right? Okay, so we have p is 10. So now we have the log of the, log base 10 of the log base 10 of x equals 10. Okay, well, again, that would mean 10 raised to the 10th power is, okay, the log base 10 of x. Okay, again, so we're saying this raised to the 10th power is the argument, and that's the argument, what we call right there. The value of x is the argument. Right? In here, the x is actually the log 10 of x. So then log 10 of x is 10 to the 10, or 10 to the 10 to the 10 is x, which is our famed Googleplex. Okay, so the solution to log of the log of the log of x equaling 1 is a googolplex. Okay? Imagine that. There you have it.